Well, who would have thought? Here we are in week 9 of the semester. We're well past the halfway point, kind of rounding the third turn here and not quite in the home stretch, but we're getting there. And so this is only really the 8th set of slides or the 8th video because week 8 really was me going over the test that we took the week before. So uh, my video, my PowerPoint says week 8, but it's really the 9th week of the semester. So let me get to that PowerPoint. I'll show you where it is. So here is here's Blackboard, right? Under lessons, right? So here's um, the top of it, right? Lessons, and I've put this right at the top of the page. Slides for week 9, the third set of slides. You won't be able to see this test 1 anymore, but you should be able to see everything else. And so the second set of slides still down there, first set of slides, but I like to put the newest stuff at the top so that you don't have to scroll all around looking for it. So by the time you're watching this, the link to this video will be above this, up at the top here. So it'll say, I guess, 9th lecture. This was a test review, is really the 8th. So let me click on that and open up these slides. So just a quick look through. Like I said, this is actually week 9. Week 8 is a little bit inaccurate. Could have changed it, just didn't feel like it. We spent the entire first half of the semester talking about basic electricity. Then we talked about computer system overview. And then we talked a lot about inputs. We had a couple inputs every week that we talked about kind of in a lot of depth. So now we're switching to outputs, and we'll start with solenoids, relays, data streams, which we covered on inputs, but we'll talk about a different part of it on outputs. Lamps and indicators like the check engine light, or even displays. On my car, it's got an issue with the airbag system, so it comes up and says service airbag, not on a light, but on a display screen. DC motors, which there are a lot of in cars. Stepper motors, which are not a lot of in cars anymore, but I'll mention how they work. And we'll talk about ignition coils. They really kind of work like nothing else. And that sort of covers almost any output on the car. It kind of falls into one of these categories. There may be some small exceptions. And, as we go through and look at stuff, I can mention those as we go. But I definitely want you to understand how all of these things work. And so we'll start with some concepts before we talk about those outputs. Direct versus indirect control. So you can read this. So let me bring up some schematics here. So for this slide, I'm using 2010 Chevrolet. Now that's not the latest and greatest, but the diagrams kind of are easier to read on these somewhat older ones. So let's have a look here. Here I have several outputs here and one input, right? So we know this is an input, the fuel tank pressure sensor, but we have the evap purge solenoid, which of course is up in the engine compartment. And that's the job of that is to take fuel vapors from the canister and pull them into the engine. I got to change the color of this highlighting here. So there we go. I like that better. That's the purge solenoid. We have the evap vent solenoid, which, as you know, is usually down under the car, somewhere in the vicinity of the canister. And then there's a fuel pump. So these are three things that are controlled by the computer. And we were talking about direct versus indirect control. Let me show you what I mean by that. So if you look here, let's look at the evap purge solenoid and vent solenoid. They're both very similar, right? Pin A on each one has battery voltage, right? B plus here. And this one, it's from the powertrain relay, but it's still battery voltage. So applied to the solenoid, and then it's wired directly to the engine control module. So here's our ECM, and these go right into it. The engine control module absolutely directly controls that solenoid. On the other hand, if we look at the fuel pump has a ground here, ground 302, right? But the other pin is connected not to the computer, but instead it's connected to the fuel pump relay up here. So this fuel pump motor in no way, shape, or form is actually connected to the computer. What the computer controls, right? The computer right here, pin 6 of the PCM, that is controlling the coil, the electromagnetic coil on the fuel pump relay. So what's happening is you have computer controlling the relay and then the relay controlling the fuel pump. That's indirect control. So you saw these solenoids here were direct control. Fuel pump here was indirect control through the relay. PCM controls the relay. Relay controls the fuel pump. So another example of direct control, this time we'll find a motor somewhere. Let's see if I can find a, all right, here's a good example. Here we have the electronic throttle body. And from this, you should remember that we have sensors, right? So we have redundant throttle position sensors sitting here. But the motor, okay, so this is what actually moves the throttle plate. That, if you look at the bottom, let me just, I'm going to shrink this enough. Hopefully you can still see it. There's a pair of switches, and are they really switches? Are they mechanical contacts inside the engine control module? Of course they're not. But that's what they're electronic versions of that. There's no actual moving parts, so they're basically transistors. And notice that one pin of the motor, right, pin 1, goes right to the engine control module, and so does pin 2. There's no intermediate, there's nothing in the way. And the way this thing works, pretty simply now, in GM world, okay, if we're looking at these diagrams, this little bar right here, right, like this one here, that represents power, right? And then obviously this is the symbol for ground. So if you look, we have two circuits, right? 581, the yellow wire, 582, the brown wire. And both of those circuits at the moment are connected to ground. That's their default position. So if the engine control module desires to operate that motor, all it has to do is take one of these, let's say pin 16, circuit 581, the yellow one here, and connect it instead to power, right? Unhook it from ground, connect it to power. Leave the other one connected to ground. So what that does is that puts, voltage on circuit 581 to pin 1 of the motor up here, and pin 2 remains grounded through circuit 582. So the motor spins in one direction. Let's just assume it's clockwise. So if we energize that circuit 581 and leave 582 grounded, then the motor's going to spin clockwise. So it can also do the other thing, right? It can leave 581 grounded, like it is here, right? And it can connect 582, the brown wire, to power. So pin 2 of the motor here has power. and then the motor spins in the opposite direction. So, now it spins counterclockwise. And, so the computer can use that direct control to move that throttle plate in tiny little increments and, open and close it. So it can energize it in one direction, open it, energize it in the other direction to close it. So that's another direct control example, right? No relay in between. So let's see if I missed anything. Some outputs are controlled directly by the computer. Some are controlled by a relay that is in turn controlled by the computer. Fuel injector is an example of direct control because it's wired directly to the computer. So of course, as I just showed you, are the evap solenoids. So indirect control example is a fuel pump. Fuel pump relay handles the fuel pump current. The relay is controlled by the computer. All right, so now this makes me figure, since I'm using fuel injectors as an example on this slide, yeah, let me just bring them up here. They're on the same set of schematics somewhere. Let's see. I'll just run on down. They're pretty much all on here. Fuel injectors, here we go. So same idea. Fuel injectors are directly controlled. So they get power from, this injector fuse, 20 amp fuse through circuit, 5291. That splits and goes to all 6 fuel injectors, that same power source, that same pink wire, same circuit number, 639. And then the engine control module can cause those injectors to open and deliver fuel by grounding whichever, so example, if fuel injector number 1 is to be turned on, then the computer creates a ground here on circuit 1744. What is that, pin 6 of the X1 connector on the engine control module. And then that fuel injector will open, fuel will spray through it until the engine control module takes this ground away, and then the injector will shut off. Directly controlled, nothing in between, no relays or anything. So that's one basic concept. You see it all over the car. Most things I would say that are low current, which is typically, solenoids, those are low current usually. Well, excuse me, lights, indicators, things like that. Those usually can be controlled directly. What causes them to use indirect control on something is if there's a lot of current flow through it, because by using indirect control, we're making the current flow through the relay and not through the computer. So you push the button on your key fob and the vehicle starts, the computer is not running that 150 amp starter current through itself. It's running it through something else, and then it's controlling that. All right, next concept in general, power side versus ground side switching. And for that, we can go right back to the all data screen that I was just on. We go back to the fuel pump and those solenoids, right? So let me open that up. And the one advantage of zooming in is that you can see things more clearly. The disadvantage, of course, is that you can't see the entire screen, and so I have to keep sliding around, right? And when I'm using this annotation tool here, I have to click it off before I can do anything with the screen. So I'll do it this way, full screen, and then I'll zoom in so you can see a little bit, maybe more clearly. So ground side switching, what are we talking about? We're talking about battery voltage constantly being available at one side of a device. So it always has power. And then the computer or something, usually the computer, is providing the ground. So when the computer wants to turn this solenoid on, it creates the ground here and the solenoid turns on. That's ground side switching. most everything in a car is ground side switched. But, you know, the exception makes the rule. On many cars, GM seems to be a fan of this particularly. The fuel pump is one thing on this GM car that is power side switched, the fuel pump relay. So if you look, that fuel pump relay has a ground all the time, right? This pin is connected directly to ground. And in order to energize it, what happens is the ECM, remember I said this little bar represents power, right? So the ECM connects that power to this circuit. And since the relay already has the ground here, right? So now we have a complete circuit and the relay energizes and current flows through the switch contacts. So again, power side switching here, ground side switching here. Ground side is much more common, but it's not exclusive. So I'll just zoom in a little bit there, you know, just so we can see evap canister purge solenoid, right? Has power, circuit 5293, pink and black wire, pin A of the evap solenoid. That has power. You turn the key on, you put a voltmeter here, you're going to find battery voltage there. In order to energize that solenoid, the computer completes this ground here, and that causes the solenoid to be energized. On the other hand, for the fuel pump, right, pin 86 on that fuel pump relay goes directly, circuit 451, black and white wire goes right to ground 111. It's always there. It's not switched on and off. If the engine control module wants to turn on that fuel pump relay, it takes this power here and connects it to that circuit, and you know, that goes up to pin 85 of the fuel pump relay. Since pin 86 is already grounded, that turns it on. All right, so I just wanted to show you that in full screen where you can see the whole thing and then zoomed in. All right. So those are just some concepts. So let's have a look. Did I miss anything? Some components are connected to a 12-volt feed and are switched on and off by connecting or disconnecting the ground wire. Whoops. And some components are connected to ground at all times and are switched on and off by connecting or disconnecting the power wire. Most outputs are ground side switched. I'd say way more than half. All right, our first output, if you remember, going back to here, I had a list of outputs we were going to talk about. So solenoids is the first one. What is a solenoid? Many of us first heard the term solenoid referred to on a starter. And that, over the years, I think has led people to be really confused because a lot of times the starter relay and the starter solenoid are like kind of like a one-piece thing mounted down on the starter, and it's a big heavy-duty thing. But that's not the only kind of solenoid on the car. In fact, that's very rare. What a solenoid is, all right, it's an electromagnet. All right, so I'll do some of my crappy drawing here for you. So you take a wire and you wrap it around a whole bunch of times and you run current through it. What happens? It becomes a magnet. If you want to make that magnet stronger, let's see, we put an iron or steel core in the middle of it. So now the wire's wrapped around that core, right? And so that's how most of these electromagnets work. When it comes to a solenoid, though, all right, I wanted to grab the core, right? I'll get it. Okay, there we go. When it comes to a solenoid, that movable core is not in the center by default, all right? It's spring-loaded outside the center of the core. And when the solenoid energizes, that thing wants to be centered. It wants to be right in the middle of that coil of wire. So as soon as you energize that solenoid, the core moves into the center. And when you de-energize it, a spring pushes it back out of the center. So in this case, it would be moving up and down. When energized, it would move down. And when de-energized, whoops, I'll get it. Can't grab it. When de-energized, it would move back to the middle. That is one crappy drawing, but hopefully it did the trick. I have actual pictures that I'll show you. Now on a wiring diagram, what does a solenoid look like? Well, we just saw a couple of them going back here, you know, they just show it like this, right? EVAP canister purge solenoid, canister vent solenoid. That's what it looks like. We had the fuel injectors. Those are all solenoids. So that's how it's drawn. But what actually is, you know, a something more like this. So here, it's kind of hard to know, but these little dots, those are actually, you know, that's a spring that's wrapped around this thing, right? So it's holding the movable core here. It's holding it upward. There's this little shelf on it, right? The spring is pushing up on that. So right here, you can see it is blocked off this port. Nothing can come out there. Okay. So spring-loaded closed. Over here, there's a vacuum source, you know, and it would like to pull vacuum on this port, but it can't because that movable core is in the way. So you can see there's 12 volts here. So what is this? Power or ground side switched? Well, it's ground side switched. The computer can connect through this transistor, can connect this circuit to ground. So what it does, and you know, this coil here is energized, right? Current flows through it. This movable core is going to wind up down in here. And because of that, this port right here will be open and vacuum will be able to flow through. So that's a really simple vacuum solenoid. But you could apply the same concepts to a fuel injector, right? So instead of a vacuum source, you know, this would be fuel pressure, and when the valve opens, fuel would spray out here. So it can be vacuum, it can be fuel, it can be transmission fluid. If this is a shift solenoid, there's just all kinds. Okay, we have two other concepts to talk about here. So there's duty cycle and there's pulse width modulation. So let's start with duty cycle. It's probably the simplest. I'm going to try to make this simple. Okay. Sometimes we don't want full flow through a solenoid. So let's just take the example of a purge solenoid. All right. I'm not saying that's controlled by duty cycle, but let's say it is. And we only want 50% flow through that solenoid. We don't just want to turn it on and have 100% flow through it. How could we do that? One way would be to try to open that solenoid halfway. And that's just not really practical to do. So instead, it's open half the time. So it opens, it closes, it opens, it closes. It spends 50% of its time open and 50% of its time closed. Let me use the example of a bucket of water, all right? So Here I have a bucket of water, and it's filled with water. And there's let's say there are 5 gallons in that bucket. If I put a valve on the bottom of this bucket, so I have a hose coming up here with a valve on it, right? And that hole is big enough to flow that whole 5 gallons in 1 minute, right? 5 gallons per minute. So if I just open it, in 1 minute, all 5 gallons are going to flow out of that bucket and it's going to be empty. If I only wanted 2.5 gallons per minute, right? Then I would just, let's see, there's all kinds of ways I could do this. I got 5 gallons. My drain flows 5 gallons a minute. So if I open it for a half a minute and close it for a half a minute, right? It's in that half a minute, it's going to drain out 2.5 gallons. If I open it for 6 seconds, close it for 6 seconds, open it for 6 seconds, I do that for a full minute, 10 times, it's only going to have drained out 2.5 gallons. That would be 50% duty cycle, either one of those. Half a minute on, half a minute off. That's 50% duty cycle. 6 seconds on, 6 seconds off, 6 seconds on, 6 seconds off. That's 50% duty cycle. So those 5 gallons would be, half of it would flow out in a minute instead of all of it. So we're controlling the flow with duty cycle. If I wanted, let's see, 1 gallon per minute, right? I would need it to be on only 1/5 of the time. I would need it to be on, 20%. So a grand total of 12 seconds out of that minute. I could turn it on for 12 seconds and then, turn it off for the other 48, but that's not how duty cycle works. See, so the way duty cycle would work is you would take that minute and adjust how often it turned on and off so that the grand total of time it was on was 12 seconds. We would lose 1 gallon. So another way I can kind of draw this, right? And again, I know these are bad drawings. I admit it. I'm almost proud of it. So if this is on and this is off, right? And they're equal, right? So this and this are the same amount of time. This is a 50% duty cycle. If I turn on and then I stay on, let's say here, and then I'm off only that much. So let's say this whole portion of time here is 4 seconds. And out of that 4 seconds, I am on 3 seconds on and 1 second off. That's a 75% duty cycle. If on the other hand, if I reverse that, right? If I am just on for 1 second, off for 3 out of my 4 second cycle, then this is 1 second and this is 3 seconds. Then this is only a 25% duty cycle, 1/4 of the time. Sorry, I didn't mean to erase that fast. And then, of course, the obvious ones, if it's just off all the time, that's a 0% duty cycle, right? And if it's just on all the time, that's a 100% duty cycle. So hopefully that explains duty cycle to you. It's a percentage. It's always a percentage. If we're not using percent, then it's not duty cycle. pulse width modulation is it's a different story. We just don't care how long the solenoid is turned off. We only care about how long it's on. So this is not a percent. It's not, you know, it's not out of 4 seconds, it's on 1, off 3, on 1, off 3. It's just, okay, we need to open the fuel injector every time that engine comes around on that intake stroke, right? So every 2 revolutions, we need to open that fuel injector. How long do we want to open it for? Do we want to open it for 3 milliseconds? Do we want to open it for 4 milliseconds? How long do we want it off? We don't care until the next time it needs to open, which is going to be exactly 2 revolutions later. That's going to be completely dependent on how fast the engine's spinning, right? But our fuel needs are not dependent on just how fast the engine's spinning. Think about it. If I'm going 70 miles an hour and I back down on the accelerator pedal, right? I don't need to deliver hardly any fuel, but the engine's probably spinning pretty fast. So the amount of time that the injector is off is going to be really small because the intake stroke is going to come around again really quickly. If I'm sitting idle and then I, you know, kind of drop it in gear, and so now it's only running at 650, 700 RPM, the off time, the time between injection pulses, now is a lot longer than it was when the engine was spinning at 3,500 RPM, right? But it may need more fuel than it did on decel. I'm sure it will need more fuel than that. So the injector on time is likely to be longer, even though the off time, you know, has changed. We don't care about that. All we care about is the on time. We don't, it's not a percentage. It's measured in milliseconds. So if you see something measured in milliseconds, then it's duty, or it's a pulse width modulated. Years ago, the only thing that I knew of that was pulse width modulated was fuel injectors. And that's why I use this as an example, right? But they've started to use it. And when I say they've started to, I mean, this has been going on for years now. To control current flow through things such as headlights, pressure control solenoids, again, in an automatic transmission. The solenoid that controls line pressure may very well be pulse width modulated. Your daytime running lights, so they're your headlights, but they're on only half brightness or less. The current running through that may be limited by pulse width modulation. So it's sending little pulses of current instead of just turning it on and leaving it on steady. To make it brighter, they lengthen the pulses. With the pressure solenoid, to up the pressure, you know, open the solenoid more, they lengthen the pulses. Fuel injector, to deliver more fuel, we lengthen the pulses. Do we care how long the thing stays closed? We do not. That's immaterial. We only care the length of that pulse. And when I say length, I mean time, you know, duration. So let's move on to the next little slide here. What is a solenoid? Oh, I guess I missed something here. Oh yeah, absolutely, definitely missed something. Back up here. So the very first screen, I guess I kind of blew through this, right? But it's kind of important. So what kind of different solenoids do we have? We have liquid control solenoids, and so examples of that are obviously fuel injectors, transmission shift solenoids, transmission pressure control solenoids. On analog brake systems, we have, you know, the isolation and vent solenoids, which I should talk about a little bit more. And so a lot of different liquid control solenoids. Vacuum and pressure, we have the ones probably most people are familiar with, evap vent solenoids, evap purge solenoids. But back in the day, so many things were controlled with vacuum, and the way the computer was able to control the vacuum was with a solenoid valve, vacuum solenoid valve. It could apply vacuum to the EGR valve. It could apply vacuum to a turbocharger wastegate, vacuum or pressure, right? So these controlled vacuum and pressure with the computer controlling the solenoid, right? And then mechanical movement, you push a button and your trunk lid pops, or you push a button and the fuel door pops. That's a mechanical solenoid. So there's two ways they can fail. So some of you in lab, I was talking about relays, and I said, just because the relay is electrically okay doesn't mean, that the coil works, doesn't mean that the relay is good. I said the click test is no good, basically. When it comes to a solenoid, if it's not working, right, it could be that the solenoid coil, the electromagnet inside, has gone bad. If you can find a spec for that, you can ohmmeter check that. Or they may be seeming to work fine. In other words, you can hear it open and close, you can feel it open and close when you energize it. But mechanically, it can be plugged. And this was a big problem with a lot of evap vent solenoids. They live in a really crappy, if you'll pardon the expression, a really crappy environment down under the car, a lot of these. And so they get dirt up in there. They can get dirt in the valve section of that solenoid. And even though electrically it's fine, it won't seal because there's dirt on the valve face. So let me go back to this slide here, right? Yeah, I'll find it. This slide here, right? So imagine that this coil is fine, right? And your wires and your control of the solenoid, all this is working fine. But for some reason, either it's mechanically stuck, something's rusty, there's dirt in there, it picked up moisture, it picked up dirt, or it's mechanically plugged, right? Or not plugged, actually, something on the seat so that it doesn't seal properly, it would actually, leak. So maybe vacuum or fluid would get through it when it's not supposed to. This used to happen to fuel injectors more regularly than it does now, but they would leak then. And so even though the computer wasn't turning them on, fuel would be coming out of them. Bad thing, right? So they can fail mechanically. Just actually verifying the electrical portion of it is not really enough. So what I like to do, and I think I have this on another slide, but to diagnose these is actually, if it's a vacuum solenoid, hook a vacuum pump to it, and then energize it and see if it changes, if it switches from, holding vacuum to releasing it, or vice versa. Which brings us to the next dot point here, right? Solenoid can be normally open or normally closed. So what normally open means is that if you pull the electrical connector off, if you remove it from the car and set it on the bench, if you buy a new one at the parts store and it's still in the box, if it's open under those conditions, then it's normally open. When you energize it, then it will close. So an example of that would be the evap vent solenoid. Its normal position when it is not energized is to allow air to flow through it into the canister. And when the computer wants to seal the system off, it energizes that solenoid, which then closes it. Normally closed solenoid, as you might guess now, right? On the bench, in the box at the parts store, whatever, it's closed, nothing flows through it. And when it's energized, it opens and then things flow through it. So a fuel injector is probably another, a good example of that as well. or the canister purge solenoid up at the engine. Typically, that is not flowing unless the computer wants it to be and energizes it. So normally open or normally closed. You might see just NC or NO next to a solenoid on a diagram. You might see it described as NO or NC, just so you know what that means, normally open or normally closed. Sorry, I missed that. Okay, so we talked about these things. So let's see, what is a solenoid? You know, it is an electromagnet with a movable core. And then the motion of that core causes something to happen. It opens or closes a valve. It moves something mechanically. It allows fluid to flow or vapor or vacuum, or it keeps it from flowing, depending on whether it's energized or not. If a solenoid comes out of the box blocking fluid or vacuum flow, what type of solenoid is it? Obviously, that would be a normally closed solenoid. Energizing it would open it. Name two ways a solenoid can fail. Let's go back here. It can be an electrical problem, or it can be a mechanical problem. So when you're testing, make sure you check for both. You know, an ohm meter is not going to find a mechanical problem, right? It's only going to find an electrical problem. What does increased pulse width on a normally closed solenoid result in? So the simple answer here is increased flow rate through the solenoid. Right? If we widen the pulse width, the solenoid is going to stay open longer. In the case of a fuel injector, you know, it's not that it opens halfway or 3/4 of the way. It opens all the way, but what controls how much flows out of it is how long it's left open. Let's talk about a bunch of examples. Fuel injector is an example of a liquid control. Variable assist power steering, liquid controlled, controlling power steering fluid. Analytic braking system, we have isolation and vent solenoids. Those are controlling brake fluid. That's a liquid control. EGR vacuum regulator, that's controlling vacuum. Canister vent, vacuum / pressure, you know. Trunk release is an example of a mechanical solenoid. And I'm not talking about the tailgate that goes up automatically. I'm talking about just the old-fashioned push a button, pop the trunk thing. And then a torque converter clutch is an example of liquid control, torque converter clutch solenoid. Let me see if I can go into a little more detail on this ABS one. Okay, so the keyboard shortcut on PowerPoint for creating a new slide is Control M, and the keyboard shortcut for muting yourself on this is Control M. So I was trying to add a new slide and I wound up muting myself. Sorry about that. Okay, so here's a blank slide, just so I have some place to draw. Now, don't laugh too hard at my lack of drawing skills, all right? So let's see. I think I can probably, yeah, I can come up with a circle. So I'm going to say that is a brake disc. And of course, you have a caliper. There's our caliper. Right? So a normal braking system without ABS, what do we have? We have a master cylinder, right? So there's the cylinder. There's a piston inside it. And then there's a steel line, rubber hose going from that brake master cylinder. And of course, here you have your brake pedal. And so when you stomp on the brake pedal, piston moves forward in the cylinder and forces brake fluid out, out here to the caliper. I know it's a bad drawing. And of course, there's a reservoir here. So I'll put the reservoir up here, and it's got fluid in it up here, right? So when the piston moves far enough back to open this port, then fluid comes out of the reservoir and fills up any empty space in here. And then when the piston moves forward, of course, it blocks off that port so that fluid doesn't push back into the reservoir when you're stepping on the brakes. All right, I'm going to get rid of most of this because most of it is pretty nasty here. All right, we'll get rid of the reservoir now. Let's just stick with the that. Now, long story short, how does ABS work? Well, we need to add in a solenoid here. So I'm going to put this normally open solenoid right in the brake line here. Normally open. Isolation valve. It's a solenoid valve. All right. Right there. So when the computer does nothing, right? Computer does absolutely nothing. That valve has no effect on the brake system. Fluid still flows through this brake line here, to the caliper, and the wheel stops. And then we have, let me just add in here, and the drawing's not going to be great, but we have a normally closed vent valve or vent solenoid. I'll just put that here. And to indicate that it is normally closed, I'll just put an X through it, right? Okay. So again, both solenoids are de-energized. So this one's closed. This one here is open, and you step on the brakes. It just the pressure from your foot from that piston goes to the brake caliper. So you're driving down the road, 4-channel ABS. So each wheel has its own wheel speed sensor, and you step on the brakes. And how does the computer know that you have a lockup situation happening? A couple ways. So one really obvious way is if the wheel speed sensors suddenly are seriously mismatched. So 3 of them are slowing down, and one of them is not, or is not slowing down as much, right? So that indicates that that wheel is locking up. I'm sorry, I said that absolutely backwards. So one is slowing down way faster than the others are. It's about to lock up, right? Or if all the wheels are about to lock up, let's say you're driving on a skating rink, right? Then when the rate of deceleration is, excessive, then the computer understands that those wheels are locking up. So let's just stick with one wheel, all right? Just one wheel is locking up. We'll say the right front wheel is locking up. So the computer knows this because that right front wheel speed sensor decelerates a lot faster, or maybe even goes right to 0. So what's the first step? Okay, is all right, that wheel is locking up. We need to stop increasing the pressure to that caliper. So let's close this normally open isolation valve. And that may be all that's necessary, right? So it energizes that solenoid, it closes, Now, all of a sudden, what that does is it blocks any further pressure from your foot, essentially making it to the caliper. Assuming that that works, that does the trick, then the computer, its next step, of course, is okay, problem solved. Oops, I erased the wrong thing. Problem solved. Let's put it back to normal. You know, let's open that valve again and let the fluid flow through. And then let's look at the wheel speed sensor again. And oh crap, it's locking up again. So we'd better block off that valve again, effectively cutting off any more pressure from your foot from hitting that brake. And because that solenoid may be opening and closing relatively rapidly, and what it's doing is it's, you know, stopping your foot from going down, but then it's letting it go down, then it stops it, then it lets it. You may feel a pulsation in the brake pedal. You may hear it. Let's say that we have a lockup situation on this right front wheel. The computer recognizes it. So it closes this normally open isolation valve by energizing it. But when looking back then at the wheel speed sensor, it sees that the wheel is still locked or decelerating too rapidly, so it's going to lock. Next step, energize the normally closed vent valve. And by energizing the normally closed vent valve, then that fluid pressure from the brake line, right? This fluid pressure here that's in the line and in the caliper already, you know, is going to be released. Now, I'm not saying it's going to spray out onto the ground like this, right? That's just plain silly. It's not. It's going to be released back into a little reservoir inside the hydraulic control unit. So all of these valves, these solenoids, are inside the hydraulic control unit. On a 4-channel, there would be 8 of them, right? So assuming then that corrects the problem, right? We've not only blocked more pressure from hitting it, we shut off this line. We've actually taken the pressure that's already in this line and we have, you know, dumped it back into the system. So as soon as that wheel seems to be okay again, what's going to happen? Well, darn it, I got the wrong line again. What's going to happen is, again, fluid is going to be allowed to flow. So that means the normally closed vent valve is going to be closed again, right? We're going to de-energize it. And the normally open isolation valve is going to be open again. We're going to de-energize it. So if you just pull the electrical connector off that hydraulic control unit, these valves are going to be in their default position, right? So you're going to just have normal braking or non-ABS braking. If you pull the ABS fuse, for example, these solenoids will be in their, you know, normal position, right? That one will be normally open, fluid will flow through it to the brake. This one will be normally closed. No fluid pressure will be dumped from that brake line. And this can happen over and over again, very, very rapidly, to where you hear it and you can feel the pedal pulsating. Now, let me just continue. What if we have a long, long ABS event? So in other words, you know, I know this isn't brakes class, but this is definitely a computer-assisted mechanism, right? So we have a long, long ABS event. That right front wheel is locking for a long time. It's on a big, long patch of ice. I suppose it would be more than one wheel would be doing this. So what happens over and over again? Isolation valve closes. That's not enough. Vent valve opens. Wheel starts turning again. Vent valve closes. Isolation valve opens. Wheel locks up again. So over and over and over again, the computer goes through this Try isolation, not enough. Try vent, okay, we're good. Go back to normal and look again. Seems a little crazy, but that's what it does. So over and over again. But the problem with that is that means that over and over again, right, this vent valve is opening, and what's happening when that's opening, right, is the fluid in this line is being dumped, and so the brake pedal, every time that everything goes back to normal, the brake pedal has to drop a little bit to push fluid back into this line because we just dumped some out of it. So over time, you know, this brake pedal is dropping, dropping, dropping. Every time this vent valve opens, it's going to cause this brake pedal to drop a little bit. That's normally not much of a problem in a short ABS event because there's plenty of travel. But if we have a long event where this vent valve has opened a lot and dumped a lot of fluid out of the system, not, like I say, not out of the system, but just back into another place in the HCU, then something has to fix that brake pedal being, you know, dropping closer and closer to the floor. And so typically there is an electric pump. So let me draw the electric pump here, right? And that electric pump can kick on and actually push fluid back into the system. And that will actually push the driver's foot back. You can feel it. You get into a long ABS event, the pedal begins to drop in tiny little increments towards the floor. And then when that pump motor comes on, you can literally feel your foot being pushed back upward as fluid is pumped back into the system to make up for everything that was lost here to the vent valve cycling, you know, maybe hundreds of times, or who knows, maybe thousands. All right, so my apologies for the really bad drawings, but hopefully it gives you a pretty good understanding of how this system works. So I am just going to erase this entire slide, I think. See if I can. And it's gone, okay. So, and then just here's an example of a fuel injector circuit. I just threw this in at the end. So let's talk about it. This thing is, it's a solenoid. So they're showing us the solenoid coil here, right? And notice we're used to saying 12 volts when we talk about battery voltage, but realistically, these fuel injectors, if these fuel injectors are operating, the engine's running. If the engine's running, it's not just battery voltage, it is alternator voltage, or I guess in the modern parlance, generator voltage. So it's 14 or maybe a little better than that, right? So notice that's being supplied to the positive terminal, if you will, of the fuel injector. So this is a ground side switch device. The switching here happens on the negative side. And in this case, it happens inside the PCM. And it is not a mechanical switch, it is a transistor. So this is a transistor. We will talk about these in more detail, but what they are basically, they're a little device with no moving parts. They allow current to flow through them sometimes, sometimes not. So in this particular one, if a small current is applied to this terminal called the base, then current is allowed to flow through what's called the emitter collector circuit to ground. So it's like a relay, which we haven't really talked about yet, but it just has no moving parts. All right, so what is a trunk release solenoid? That would be a mechanical solenoid. And what kind of a solenoid is a fuel injector? That would be a liquid control. What else would be liquid control? Things that control brake fluid, things that control transmission fluid. A more recent example, really common now, vehicles have variable valve timing. So there will be solenoids for the cam phasers controlling the flow of motor oil into a cam phaser, which can then advance the cam. So how do I diagnose a solenoid? Well, for electrical failure, uh, checking for voltage, uh, both power and ground. Usually the easiest way to do this is to unplug the solenoid and put what's known as a Noid light in, right? So a Noid light, I'm assuming Noid is kind of short for solenoid, right? But what it is just it's a little light that you can plug in place of the solenoid. Now what you do is you go to your scan tool and you go to your output controls on the scan tool and you command that solenoid on and you watch for the light to light. If that light lights, then you know the control circuit is working fine and the problem is in the solenoid itself. If that light does not light, then you don't think it's the solenoid, you think there's a problem with the control circuit. So that's a way to check the circuit. And then to check the solenoid itself for continuity / resistance, you're wondering, is the coil broken inside it? The only problem with checking resistance on it is you either need a specification or you need a known good one for comparison. Well, what I've done a lot of times, take a little 9-volt battery, that's usually enough, a couple jumper wires, and as soon as you touch that 9-volt battery to the solenoid terminals, you're probably going to hear it click. Then you're going to know electrically it's okay. As far as mechanical failure, that can be a little more challenging. On a vacuum solenoid, no problem. Blow through it, get a vacuum pump. If it's normally open, then you should be able to get flow through it until you energize it. And if it's normally closed, you should have no flow until you energize it. So if it's a mechanical solenoid, obviously you can just watch it to see if it moves. If it's a fuel injector, a little more difficult because those are typically inside the intake manifold, inside the fuel rail. If you remove it from the car and try to test it on the bench, then you don't have any fuel pressure attached to it. So we can do things like injector flow testing. I think you probably did that in fuel and emissions, where you check the vehicle's fuel pressure and then you energize an injector and see if the fuel pressure in the rail drops. It should. If the injector is open, letting fuel out of the rail, the pressure should drop. If it doesn't, then injector's not flowing. And you can actually even check for the correct amount of flow, or at least that they're all the same when it comes to a fuel injector, by just comparing that pressure drop on it. That's something, like I said, we're not going to talk about that in detail. It's something you should have done in fuel and emissions. I think we did it in engine performance class 2 last year. Okay, we have been over an hour now, so I am going to kind of just wrap it up here. Right, so here's what we talked about. We talked about power side switching and ground side switching. We talked about direct control and indirect control, and I think I told you that indirect control is usually used for things that are high current draw, like motors, cooling fan, fuel pump, power window motors, things like that. They're typically going to run through a relay, and then a computer is going to control the relay. Smaller loads, like for example, that throttle actuator motor I showed you, that was wired directly into the computer, no relay involved. That's direct control. Solenoids are typically direct control. We talked about duty cycle and we talked about pulse width modulation, and then We spent time talking about solenoids in general and some solenoid examples in particular. I did some horrible drawing for you, but sometimes it's not the quality of the drawing. Sometimes simplicity of a drawing actually makes it easier to understand what's being said. So hopefully that's the case. I don't know. If not, it sounds good. So next week we'll move on to relays. You have all the slides. I mean, you go on Blackboard, obviously, and I posted the slides there, so you can look ahead if you want. But that's what we'll be covering. The slides starting with relays next week. In the meantime, I'll see you out in the shop, and today's Friday, so have a good weekend.